So we can, I can move off that now, right?
Yeah, yeah.
I move off that, okay.
So if you just change it back to .cam or whatever you want.
Back to the .cam. And just very quickly, we didn't calculate everything because we left that for you. But the idea is that sampling with replacement, the probabilities of a red on the second pole is the same as the probability of a red on the first pole. Similarly, the probability of a white on the second is the same as the probability of a white on the first. But the point is, you've got two different ways of getting one red and one white. You can either get the red and then the white. 3/5 times 2/5 is 6 out of 25. Or you could have got the white and then the red, which is 2/5 times 3/5 is 6/25. 6 out of 25 plus 6 out of 25 is 12 out of 25, or 0.48. Okay, so one of the rules we've used there is this very simple equation, probability equation for disjoint events, and I need to go off of the .cam again and go to the laptop. Sometimes I forget that. And let me just get this to go. That's odd. Oh, I know what the problem is. It's got to be this.
You probably want to do the FNF7
That was
again.
it. That was it. Okay. And let's see. It's partly there, but
Yeah, I guess you gotta hit home and you see mine on the left side of the screen.
oh yeah, it's got both sides. Right. Right. Okay. Good stuff. So one rule we use, and you may have just done it intuitively without really thinking about it, is that we had two disjoint events when we asked for the probability of one red and one white. The disjoint events were getting a red on the first and a white on the second, so that was one event, and getting a white on the first and red on the second was another disjoint from the first one. What we simply did was add those two probabilities together. We do this constantly. You know, you're doing it when you do dice experiments. You said, you know, what's the probability? The sum is no more than 4, for example. And so you say, well, this is the probability the sum is 2, plus the probability the sum is 3, plus the probability the sum is 4. And in a sense, we even use that rule when we get the event the sum is 3. We said, well, the sum is 3. We could have got it with a 1 and a 2, or a 2 and a 1. Okay? So you use this rule very, very frequently, and it's something that just kind of occurs intuitively with people. Just summarizing, we have discussed conditional probability, and just summarizing a couple of equations on this that we'll kind of come back to. And conditional probability is challenging. We kind of have a rule in second-year statistics classes: if you want a challenging question, just make it a conditional probability question. So what we want to do is that you're going to feel really comfortable. We're going to take it at a pace, illustrated with enough examples that you feel comfortable with the idea of conditional probability. And we're going to see that, in fact, the probability of A given B is the probability of the intersection of A and B over the probability of B. And one of the ideas that came up, and Mihai kind of emphasized this idea that there is a restricted sample space with conditional probability, that if our original sample space is S, but you're given that the event B has occurred, then we restrict our sample space just to the space where, in fact, B has occurred. And then we ask ourselves, what is the proportion of the event B which contains A Well, that area in the sample space S is A intersect B, and so we're saying what is that proportion within B, which also has A in it, that is the intersection of A and B over the probability of B. And you can look at reversing that conditional probability, but now A being the restricted sample space, so if I ask for the probability of B given A, it's going to be the probability of A intersect B over the probability of A. So right now these are just equations that need you to see them in a somewhat deeper way, but we could go back to our very first example with the urns. Go back to the very first example with the urns, and let's go, well, let's go both of the dot cams there. Dot cam on both. And it's got it. Okay, so we saw here, for example, that the probability of R1 intersect R2 was the probability of R1 times the probability of R2 given R1. Okay, fine and dandy. But, you know, if I get another piece of paper here, again, we found that the probability of R1 intersect R2, we did it by taking the probability of R1 times the probability of R2 given R1. But if we wanted to write this, rearrange the mathematics of this a little bit, we could say the probability of R2 given R1 is equal to the probability of R1 intersect R2 over the probability of R1. Okay, so again, the thing after the condition is our restricted sample space, and kind of some small mathematics. We also noticed at the bottom, which is off the screen now, so let's go back to the laptop again. Back to the laptop. We use this rule, the probability of the intersection of A and B. We took in this case, the probability of R1 times the probability of R2 given R1 to get the probability of the intersection. We're going to use this there that we went through a time sequence there where we said, here's the first ball, draw the first ball, and then draw the second ball, given we've done the first ball. And that can be reversed, and sometimes we will put things in reverse, and I might have said, well, it's the probability that the second ball is red times the probability the first ball is red given the second ball is red. That seems like a weird thing to do, but we will find that we have interesting applications for that. So we have a very special relationship between events, pairs of events, if the conditional probability is the same as the unconditional probabilities. And if the probability of A given B is simply the probability of A, then A and B are independent events. A key idea of independent events is that knowing the occurrence or non-occurrence of one event, it gives us no information about the occurrence or non-occurrence of the other event. So when we sampled without replacement, the probability of a red on the second ball was dependent on whether or not we got a red on the first ball. But was that the case when we sampled with replacement? When we sampled with replacement, whether or not we got a red on the first ball, did it affect the probability of a red on the second? It did not. Okay? So knowing what you got on the first ball, it wasn't going to tell you anything about the probability and a red on the second were independent events. And when you've got independent events, for example, the probability of B given A is just going to be the probability of B. We get this simple multiplication rule that we can get the intersection of the two independent events by simply multiplying their two unconditional probabilities. Now, here's what to watch for. Lots of people do this automatically, even when the events are not independent. Okay, and so sometimes you get into a situation you just say, well, how do I know if they're independent? What if it doesn't tell us that they're independent? Sometimes they'll tell you they're independent. Sometimes they can be what I call structurally independent. We can infer that if you roll die 1 and you roll die 2, what happens on die 1 isn't going to affect what happens on die 2 and vice versa. So the outcome on die 1 is independent of the outcome on die 2. That's a reasonable thing to assume. In some problems though, you might be given enough information to test whether the events are independent. Okay, we'll give you some examples of those as well, that you've got to check certain other probabilities to test for independence. Now, this is kind of a long slide. It's kind of why I wanted to pre-post on this, is that one of the interesting things when we've got like an A complement, a B and a B complement, is if A and B are independent, so are A and B complement, so are A complement and B, so are A complement and B complement. And if you can find any pair of A with B, A with B complement, A complement with B, or A complement with B complement, if you can find any pair of them to be that you have proved independent, you will have proved it with all pairs, okay? So, so if A and B are independent, so are the events and their complements. And if they're not independent, we say they're dependent, okay? So we're going to keep trying to emphasize that kind of idea of being able to recognize independence and how to test for it, how we're going to use it to simplify some of our problems. So let's just take a look at the summary of the 3 red, 2 white urn problem so far. We went through, we did it without replacement, we did it with replacement, and so we performed probability experiments where 2 balls were chosen at random from an urn containing 3 red and 2 white balls. And in the first experiment, sampling was conducted without replacement, and in the second experiment, sampling was conducted with replacement. And with the aid of probability trees, we calculated the probability of getting each possible outcome, where we kept track of the color on each pull from the urn. And for each experiment, we calculated the probabilities of getting 2 red balls, 2 white balls, and 1 ball of each color, of which the 1 ball of each color, we recognized that it could have been red on the first, white on the second, or white on the first, red on the second. We had to combine those 2 possible ways of getting 1 red and 1 white to answer the question, 1 ball of each color. And we attached algebraic notation to the probabilities in each tree. And the question I have here is, why could we simplify the notation when the sampling was with replacement as compared to sampling without replacement? And the key idea is, think of that key idea in your brain. What is he going to say? Is that when we sampled with replacement, we got independence between the second pole and the first pole, and the independence between the poles, between the successive poles of the balls, really simplified the problem tremendously. Now, we can extend earn problems in all kinds of ways. There's some incredibly mathematically difficult books on earn, what they call earn models, where everything's based on pulls from an earn. And so let's just kind of think about a few of the ways that we could extend those earn problems. One is there could be more than 2 colors in an earn. Now,
Where would you buy an urn with more than 2 colors?
where would you get a urn with more than 2 colors? There's my urn. Now, let's just look at these things. Hard to focus on there. This is a genuine urn. It has got holes in the bottom. You may say, why is the holes in the bottom of your urn? I'm afraid that's like, you wouldn't hold things. Well, the reason there's holes in the bottom of the urn is you have to let the eye juice drain away. And this is what is in my urn. And let's just see if we can see this. These are very frightening balls. They are eyeballs. These are genuine eyeballs. I know they're genuine because I bought them at Dollarama. And you get 8 of them in a package. 8 of them in a package for only $1.25. So for $5 I got 4 packages, which gives me 32 eyeballs. Some packages are all white, so I have 8 of those, and then some packages had 3 purple, 2 orange, and 2 green. They're all 6 packages I checked, and it was always the same ratio, 3, 3, 2, so they're made up that way, not random, okay? So you see, oh my goodness, my balls are getting away. Okay, stay. Okay, so anyhow, think about this problem. You know, if I've got a certain number of balls of each color here, and I've got more than 2 things, I can go in and I can ask questions like, if I had 4 colors of balls, so many of each, I can say, what's the probability when we select them that I get exactly one of each color? What if I ask, what is the probability at least 2 of the balls are orange? We're going to have a bunch of these. And some of them have fairly hard answers. Could you believe they have fairly hard answers? Some of them have fairly hard answers. But that's kind of an interesting idea, that we've got multiple colors, and if we had multiple colors, we could think about, you know, how are we going to have to change our notation? You don't, for example, well, we did red and white, we could do that, we could have a letter for each color, but if we're kind of thinking of our sample space as not just a case of, well, white was the complement of red, but now we partition our sample space into 4 different colors, right? We've got 4 different colors. I can add any number of colors. And so we can have more than 2 colors in an urn. We're going to, against to that, we can have 2 or more urns.
Do you want to put the HDMI back?
Oh, back to the HDMI. Yes, thank you. Yes, you've got to keep an eye on me on this. I need a system that thinks automatically what I want to do.
That's what the students are for.
That's what the students for. Okay. Yes, that actually does work well. Oh, I should mention, if you've got a question for me and I'm not seeing your hand, you see, I go with the business of, because I hear better than I see things, and so that one can draw my attention. Okay, so where we got 2 or more urns. So we could have you pick one of the urns via some random process, and how you pick those urns might occur with equal or unequal probabilities. And we might get weird things like, to pick an urn, you roll a die. And if you get a 1 or a 2, you pick urn 1. If you get 3 or higher, you'll pick urn 2. Or maybe you got more than 2 urns. And maybe you got 3 urns. 1 or 2 get you earn 1, earn 2, maybe 3, 4, and 5, and getting a 6 gives you earn 3. And then you can have different numbers of balls in each urn. So you can see where these things would get tricky. And we can do unusual things on each pull. So here's an example of what a kind of an unusual thing. Consider the following experiment. A ball is pulled at random from an urn containing 3 red and 2 white balls. The ball is recorded, and the ball is replaced by a ball of the opposite color. So what does it mean by the opposite color? If I pull a red, I replace it by a white. If I get a white, I replace it by a red. A second ball is pulled at random from the urn. What are the probabilities? Both balls drawn are red, both balls drawn are white, and one of each color is drawn. We're going to have a mathematized question coming up here. So you might want to start thinking this through as quickly as you can, but I'm going to help you set it up. I'm going to help set it up. Well, let's give you a minute or so to set up the problem. Think of setting up the probability tree for this one. Okay, so we're going to set up the probability tree just like we did for the previous ones, but now we've got this somewhat more complicated experiment. And on this one, feel free to collaborate. If you feel like you're not getting anywhere, this is why you come to a class with really bright colleagues. You just ask the people beside you. I'm just going to give you a minute or so to kind of think of the problem, get started, and then I will go on to the dot cam.
Sure.
Partly draw the tree.
Yeah, when do you want me to open the question?
I will let you know.
Okay.
I'll let you know. Time-wise, I feel like we're not doing too bad.
No, I think you're doing good actually. Yeah, we got a good quick start today.
We did. A lot of things went in at the start. Let me ask, anybody think they got the tree finished? Oh, we got a few that think they've got the tree finished. This is good, this is good. Okay, gonna give you 30 seconds more, and then I'm going to start drawing the tree, and I'm not going to finish drawing the tree. I am heading for the dot cam. Okay, we started off 3 red. And then I did my first pull. And I said I either get a red or a white. No problems. What's so difficult about this? 3 fists for that one, 2 fists for a white, 3 fists for a red, 2 fists for a white. Now, the next thing is, and this is where pictures are very helpful to you, is that was the first pull. Then I'm going to do the second pull, but things change in kind of interesting ways here. And one of the things to do is perhaps draw a new urn. For this one, Cause if I got a red on this one, I'm gonna end up with, what am I gonna end up with in here? What do you
You
got?
have 3 reds and 2 reds.
Yeah, I've lost a red, but I've gained a white. So looking at my choices here, my chances of a red are going to be 2 out of 5. My chances of a white are going to be 3 out of 5. Okay? And similarly, then I also recognize that the urn needs to be updated if I got a white there. And if I got a white there, what am I ending up with in the urn? What do I get in my urn? What did you get in your urn?
4 reds, 1 white.
4 reds, 1 white. Absolutely. Okay, so go red and then white. Now, this was, so this is now going to be 4/5, and this is going to be 1/5.
Gary, you're 1/5 snuck off the bottom.
It is off the bottom. Okay, that is outrageous. I am outraged when that happens. Okay, so let's get the intersections. You can go through, label this R1 on this first, R2, you know, this is the probability of R1, this is the probability of R2 given R1. This is the probability of R2 given R1. Nothing about wrong with that. That's the probability of R1, and you can go through and finish the rest there. But the intersection, the probability of R1 intersect R2, you are taking the probability of R1 times the probability of R2 given R1. And so you're taking 3/5 times 2/5 is 6 out of 25. Now, you can work out the rest of the intersections there. We're going to give you a moment for that, but now comes the mathematized question.
Do you want to head it over to USB?
You can.
You have to press the button.
What do I have to do?
So like switching to
I have to go to
HDMI.
web conference, yes. Got
Yes, that's the one. Okay. Let's see. Okay. So here we are. In the more complicated urn model, what is the probability of getting one of each ball? So same question that we started out the class with, but now it's the more complicated urn model. And we're giving you a hint here that the answer is something out of 25. But we want you to just enter in the top of the fraction. So it's some whole number out of 25.
That's one of each color of ball. One of each color.
One of each color, yes. Maybe you should tell them when you want to stop. 2 minutes or something. Do you want me to put a timer on?
We'll monitor it after 2 minutes.
Okay.
2 minutes is probably good. Try to get that in within 2 minutes. We'll probably take a 15-second to get your final answer in. So that's been running for a minute already.
Just 1 minute, yeah. So,
Or will we be talking during that?
no, so there's a little timer and it tells you.
Right.
It's been a minute.
But
and
was
10
that
seconds.
timer is immediately when you open it or when you
That's
stop?
that's true. That's when we immediately open it.
Right.
Okay, let's do. Let me see if I can get this up. Okay.
based on my sample so far, unless all like the whiz kids are all along
This is
the
a
edge.
biased sample.
Yeah, bias sample.
Well, the people who don't know the answer don't put their hand up.
Well, they didn't get a chance to put their hand up. I just went and asked them.
Okay. All right, get your answers in. Only a couple seconds left. If you don't know the answer, take a guess. All right. All right. Out of 92 people, 78 people said 17. Last time we said there were 2 branches. So you got to add one branch to the other branch. So the answer should be an even number. You're adding something to something else. Why did everybody say 17?
Ah.
The correct answer is 17. Oh my goodness.
Okay, let's just go through. What happened there?
I've been bamboozled.
You've been bamboozled. There we go. Okay, so we said we could go red and then white. So that is going to be the probability of a red on the first and a white on the second. Is the probability of a red on the first times the probability of a white on the second given a red on the first is going to be 3/5 times 3/5 is going to be 9 out of 25, or we could get the probability of a white on the first and a red on the second is going to be the probability of a white on the first times the probability of a red on the second given a white on the first is going to be 2 out of 5 times 4 out of 5 equals 8 out of 25. If you wanted to work out the final one, let's just work out the final one. White on the first intersected with white on the second is the probability of white on the first times the probability of white on the second given the white on the first is 2/5 times 1/5 equals 2 out of 25. Those intersections add up to 1 as they must, because those intersections are 4 mutually exclusive or disjoint events that are also exhaustive of the sample space. So one of those intersections must occur, and we want to take the 9/25 and add the 8/25, right? So red on the first and white on the second versus white on the first and red on the second, they don't have equal probabilities here because of the nature of the experiment, the business of replacing one ball with the other. So that can kind of mess you up a little bit, but again, you reason it through. 9/25 plus 8/25, 17 out of 25. So you've done a pretty challenging question. Okay, so at this point you're saying, Humphrey, have you got any more challenges for us? Give me a challenge. So I'm not going through these problems right now. We will get answers at some point. Yeah, so many more possibilities of what I can do with these things, what we can do with these things exist. But here's a couple you might want to try with the 3 red balls, 2 white balls urn experiment. Try these on your own. So same experiments as before, do them both without and with replacement. And what's the probability at least one ball drawn is red? Okay, I think that's an easy answer for you. Okay, easy one to solve. What's the probability the first ball drawn was red if the second ball drawn was red? I don't think that is an easy question for you, and in fact we will be treating this kind of problem at greater length in the future. But many people can do this without knowing the formal approach to this kind of question. What is the probability the second ball drawn was red if we don't know the color of the first ball drawn? That's such an easy question when we sample with replacement. What happens if we sample without replacement? If we sample without replacement, we know the probability the second is red depends on what we pulled on the first ball. Because that probability of the second is red is one probability if the first ball drawn is red, and it's a different probability if the first ball drawn is white. So how are we going to answer that question? Wicked. Wicked. Bit wicked. And adding another good challenge here. If it is known that at least one ball drawn is red, what is the probability that both balls drawn are red? Something else. So these are on your own. These are on your own. I'm not going to belabor them right now. Okay. So we're going to start and go through relatively quickly two by two tables, and these are kind of nice to have up ahead of time. So basically the tables consider something like 200 people, and they've been classified by two trades. There's a trade A and a trade B, and I'm not going to say what's the trade A and what's the trade B. Maybe the first trade is whether they people classify themselves as female or not female. B is whether they are blonde or not blonde, for example. I am clearly platinum blonde. Yes. But you can make whatever two traits you want. You can think about kind of different traits on these tables. So we're going to obtain probabilities of various events for a randomly selected person from the group of 200. And for each case, what's the relationship between events A and B? What's the relationship between A and B complement? So our very first one is this table here. 200 individuals, of which 150 of them exhibit trait A, 50 of them exhibit not A. And for trait B, there's 120 of them exhibit trait B, 80 of them do not exhibit trait B. So, yes, 200, but you've got 4 intersections in there. Notice you've got 4 intersections. So if we ask what's the probability that a person exhibits both trait A and trait B, you would say, oh, that's 90 out of 200. Okay, so very quickly, we can go through and ask these particular questions. And we're going to kind of work through a little of these. I'm going to freeze one screen on this one here, and I'm going to just go back to the table here. And let's just kind of go through and say, hey, how would we get each of these? Probability of A, you pick a person at random from the table. 150 have trait A, 150 out of 200. Bang. Trait B, probability of exhibiting trait B, we go to our table and we go, there's 120 that exhibit trait B out of 200. Okay, bang. 120 out of 200, that's 0.6. Got it. What else did I ask? The probability of A intersect B. So they've got to exhibit both trait A and trait B. And so that's 90 people. 90 out of 200. Bang. The intersection is 90 out of 200, 0.45. What else did I ask? The probability of A given B. Okay, now this is where it gets kind of interesting. Probability of A given B. Okay, given that we are in B, we restrict our sample space to those who have trait B. And so our answer for A given B is going to be 90 out of 120. 90 out of 120. Bang. 90 out of 120. How about B given A? B given A, given a person has trait A, we restrict our sample space to those 180 individuals here. And 90 of those also have Trait B, 90 out of 150. Bang. And we can fill in a couple other values there. I'm going to let you look at those values, but I'm just kind of keeping an eye on my time at the same time. And there's the answers. Okay. Oh, no, those aren't the answers. Okay. Yes, those are the answers.
Still frozen over there.
Oh, it's frozen. That's my problem. Okay, frozen. Okay. Now, a question: are A and B independent or dependent? They are independent because the probability of A is equal to the probability of A given B. B gave no information about A. So we're going to spend a little more time on this at a future time. I'm just going to show you one more table. Same marginal totals. Same set of questions. And you might want to work through it beforehand if you've got the chance. Okay? And that's it for today.